Silicon Valley Future Forum.
Now, so my interest is in visual computing, which is computer graphics and vision. Graphics is a synthesis problem, vision an analysis problem, but they share the topics of images and videos and mathematical models. So starting with mathematical models, computer graphics synthesizes images. Computer vision goes the opposite way to analyze images and build models of what's in the image. So they're very compatible fields, and synergies in working with both of them is something that's very interesting these days. So my talk will talk about AI and machine learning and computer graphics, and then switch over to computer vision, and then perhaps, if there's any time, trends in the future. Now, one of the important aspects of computer graphics is physics-based animation. So something like this is state-of-the-art animation. You can see it's DreamWorks. This is done by researchers in my lab, and it's being used in the industry. This kind of simulation requires simulating Newtonian mechanics, the differential equations of physics. It's very slow to do this sort of thing in general. So there's an opportunity to actually use machine learning to actually learn physics, which might seem very strange that it could be done, but it does work. The neural network emulator, we all know about neural networks, I hope, here, so I don't have to talk in detail about this, but learning physics for a network amounts to basically taking the simulation and generating training data from the simulator. So here you have a state of the pendulum before and a state several milliseconds later. And then you create more random states like this, state transitions, feed that training data to the neural network. What the neural network is doing is regression, basically. It's fitting a non-linear model to the training data from the initial state to the next state or final state. And once it's learned basically the behavior, then it can emulate the behavior much faster than the physical simulator. Now let me move on to the state-of-the-art of computer graphics in terms of characters. So in games and in movies, these sorts of characters are not alive in any sense. So they're just basically graphical puppets, and they're animated using motion capture technology these days. But it's possible to actually build artificial life models of humans and other animals. We start with physics and biomechanics to produce locomotion, and then we put perception, behavior, learning, and ultimately cognition models in a stack of models that, and then these parts is what's known as artificial intelligence in general. And so with these models, we can actually build a working human, virtual human that can swim in water, as you see here. Again, I have to click on this, unfortunately, but hopefully, let's say this plays. So here's our human swimmer in a simulated fluid, and it's able to control its body to do various things that swimmers do in water. Okay, let me move on. Now, this is a model with a brain and central pattern generators that control the muscles in the model. Let me not bother with that one. So here's our model of the human, and you could see the muscle actuators. There are actually 846 muscles in this human model, and soft tissue using finite element methods. And you can see here the muscle structure, forward and backwards. And here's a rendered version of the muscles themselves. And finally, the skinned model. And this is now capable of working the way a real human does. Now, so here you can hopefully see the inside. You can see the muscles working to actuate the bones and so on. Now, to give you an idea of how do we control complex models like this? Well, the natural way is through neuromuscular control, the way it's done in the real body, whether it's human or animal. And can these models actually learn to control themselves? The answer is yes, just the way we learn how to control our own human bodies. Now, let me give you an example of this from the point of view of just the neck. You see the complexity of the neck in a real human. And we have simplified model of that, but it's still quite complex. I'm not going to go through the equations here. When you turn on physics with the bones, you see that the head just collapses. So we have the muscles that control the neck over here. And now the question is, how do we train the brain to be able to control these muscles to make controlled head movements? So this will require neural networks. Here's just showing the various muscles. There are actually 72 neck muscles over here. So the big challenge is how to co-activate the muscles and control them. Leonardo da Vinci versus our model. Quite similar, actually. Now let's see. So here's our system. We have muscles, we have neuromuscular controllers, and then the skeleton and the biomechanical model. And so the question is, how do we build controllers that can actually learn to control this neck, head, face model? So the way we do this is give it random visual targets, like this little doll. And then if we solve what are known as inverse kinematics and inverse dynamics problems, which are slow, we can generate training data. And once the training, so again, with lots and lots of training data, if I can see, lots of training examples, and we can generate unlimited quantities of these training examples through our simulator. Now, once the model has learned what the simulator is doing, then it should, does the regression, the neural network model, and let's see if this works. Let me click on it again over here. There we go. Now the model has learned to control the head in gravity and do controlled head movements. Okay. I have to abbreviate this talk. Now let me move on to rendering in computer graphics. Let's look at the problem of texture mapping. A surface is very complicated. So an ordinary texture map on a 3D surface looks kind of, too simple. But we can actually learn how a surface appears under various lighting and under various illumination and from the different points of view of the surface, the way we're looking at it. And we can build a machine learning model that takes the observations, uses a technique here we call tensor decomposition, and then builds an appearance, a generative model of the appearance of a complex surface texture. And then this can be rendered. And the texture here depends on the viewpoint and the illumination. So it's a non-constant texture model. Switching over to face recognition. This is a very difficult problem in biometrics. And the reason is because under different illuminations and viewpoints, faces look extremely different. And so, again, but if we have training data of how a person looks under various and different expressions and so on, so we have what's known as a PIE data set, pose, illumination, expression, etc. We can give this training data to organize it in terms of a tensor. You see here, a tensor is an n-dimensional matrix of data. And then with the appropriate tensor decomposition methods that actually generalize matrix decomposition, we can build a model that has what we call a tensor faces model that can actually recognize faces irrespective of the lighting and viewpoint conditions. It's very robust against that. So this is, again, another example of using machine learning. Now let me switch to kind of over to computer, other aspects of computer vision. I could talk about, for example, driverless cars and things like that. I won't do that. Mobileye and other companies are actively working on that with much success involving learning methods. But let me talk about model-based medical image analysis. So in a sense, this is kind of a little bit older school, although this particular model is quite innovative in the sense that it has, you create a model of something that's of interest, let's say in a medical image. This is a slice of a brain, and the corpus callosum is this gray area in the middle that connects the left hemisphere and the right hemisphere. And for purposes of, neuroscientists are interested in schizophrenia and so on, want to know what is the shape of this corpus callosum. And so what we've created here is an AI model that has a simple brain and knows how to look for the corpus callosum and reconstruct it. Okay, it has a mental model of what the corpus callosum has, both anatomically and medically. And here it is, it's running. And you could see it's like a little organism. It goes into the image and it discovers where is the region of interest, and then it grows itself into that region of interest to, this is slowed down a lot, and maybe I shouldn't let it play all the way through, but the idea, as you could see, is it grows itself using the mental model of what a typical corpus callosum would look like, and it's able to do a precise segmentation of the region of interest and get quantitative information about the shape and other aspects of this particular region. Okay, so it's adjusting itself further now. I'm just going to move on in the interest of time. So now I think in terms of medical imaging, there's a vast business opportunity here. It was mentioned by our previous keynote speaker, who did a great job overall in kind of laying out the industry interests in AI and machine learning. But from the point of view of medical imaging, there's exploding data volumes that doctors need to look at. And on the other hand, there's a manpower shortage. I mean, we are all familiar with this. As imaging devices get better and better, they produce more data. That data has to be analyzed, and there aren't enough doctors in the world to actually do a good job. So what we're interested in is evidence-based diagnosis in an automated manner to be able to do disease screening, at least, if not diagnosis, longitudinal tracking of how patients respond to medications and so on. Basically, and also deal with the experience shortage of doctors. So we're not trying to replace doctors. That's impossible today. Maybe sometime way in the future it might be possible. What we're trying to do is actually give tools to doctors that will increase their productivity quite significantly. So what we've been looking at is, of course, AI and specifically deep learning in order to gain automation, accelerated insights, analytics basically, and diagnostics from medical data. And for example, lung cancer. This is one of the this is the deadliest cancer worldwide. Early detection is critical, but again, there aren't enough doctors for all the patients, especially in high population countries like China and India, to examine all patients at an early stage. So the tools are required for automating this to some degree, to give doctors a second opinion or maybe a first opinion, and then the doctor comes in and verifies what the automated system is suggesting or recommending. So we've been looking at applying deep, in this case, convolutional neural networks to the problem, and we've had quite a bit of success in doing that. This is in the context of a startup company that we call Voxel Cloud. You can see our capitalization here. And this is a company that's essentially 1.5 years old now, and we've had quite a bit of support from these firms, and we're at kind of like the, let's say, $100 million level already in terms of valuation. So what we are building here as a first step is a screening platform that involves, big data for acquiring big data infrastructure deployed on the cloud, for acquiring training data from many case histories, not just image data, but also medical records, combining the two together using machine learning methods, among them deep learning, of course, and being able to generate reports and insights that physicians and other doctors are capable of utilizing and will increase their productivity quite a lot. So there are other, of course, opportunities in medical imaging, a large number. Retinopathy was mentioned by the previous speaker. We're also looking at coronary heart disease and other types of applications. And the CEO of our startup company, Dr. Xiaowei Ding, will be giving a talk in the next session telling you more about this. So to finish up my very quick presentation, let me just conclude by saying there's enormous, I think there's enormous potential of computer science and specifically of AI, and of course all the basic information technology infrastructure that's already in place. All of this coming together will create a revolution in medicine and healthcare. And I think we're just at the beginning of this very important trend right now. And I think there's going to be explosive growth in this in the near future. Of course, a great deal more research must be done to enable this. What we're seeing, again, is just the beginnings. And this research, of course, is very challenging. And I don't think machine learning is the answer. I don't think it's a silver bullet that'll solve all problems. We're going to, in the future, require the assistance of and hybridization of machine learning methods and older model-based techniques to come together to get to the next level of performance. And so I think this is a very exciting time, as has been mentioned already. And it's great to be able to be a part of this in some meaningful way and actually to be able to profit from it. So I think I'm done at this point. If there are any questions, I'll be happy to answer them. Okay.
Silicon Valley Future Forum.